Hello, linear algebra students. Today's video lecture is on linear transformations. Now, a transformation is a function, capital T, that maps a vector in Rn, which we call the domain, to a vector in Rm, which we call the codomain. Now, n and m don't have to be the same number, or they could be the same number. Now, we use the notation capital T, colon, Rn, arrow pointing at Rm to establish this mapping. So imagine we have a space. I'll represent with a circle here, Venn diagram. And this space represents all of Rn. And we take a vector in it, and it maps to some vector in another space, which I'll represent with a circle as well, and this will be Rm. The vector we began with in Rn we'll call vector u, and it maps to vector v in Rm. So linear transformation just takes one vector to another vector. It's very similar to any function that takes an input and turns it into an output, except that the inputs and outputs are vectors now. And continuing to read right here, we can use function notation to show that the vector u maps to the vector v. U is called the input vector, or sometimes called the pre-image of v, and v is called the output vector, or the image of u. The set of all images of a transformation is called the range of the transformation. Now, the range and the codomain don't necessarily have to be the same thing. Suppose all the vectors in Rn map to only a portion of Rm. We'll call that portion a smaller Venn diagram in here. And every single vector in Rn that you begin with takes you to somewhere inside that orange circle. The orange circle is the set of all possible images of all the vectors u that are in Rn, or it's a set of all possible outputs. This we're calling the range, and it doesn't necessarily have to equal the entire space Rm. For each transformation below, find the images of some inputs and identify the domain, codomain, and range. Okay, looking at this first example, we have a transformation we're calling t sub 1. It inputs a vector x, y, and it outputs a vector with 3 components. So let's input a few example vectors here. Let's input the vector 2, 1 and see what happens. So x is 2 and y is 1. Plug that into the equations you see in the output vector. For the first component, we would get 3 times 2 and then plus 1. That's going to give us 7. The second component, just change the sign of the y-coordinate of the input vector, so that'll be negative 1. And the third component is always 0. Let's try this again with a different input vector, just for variety's sake. Let's input negative 1 and 3 for my xy vector. This transformation will turn this vector into a new vector. Plug in negative 1 for x and 3 for y, and we get 0 for the first component. We get negative 3 for the second component, and 0 again for the third component. So this transformation will only yield vectors that are in the xy plane in 3 space, because the bottom component is guaranteed to always be 0, and that's the z component of the output vector. Furthermore, you may want to ask yourself, is it possible to get any vector in the xy plane? So let's just make one up. If I say I want this to be 8 and this to be 5, of course the bottom would have to be 0, because we can't get a non-zero down there in the third component. But is this a possible vector? Could I find the pre-image of this vector? In other words, the input vector. In other words, what would I input into this transformation to get 8, 5, 0 back? Well, we know the middle component of my output vector has to be the opposite of the second component of the input vector. So we know that we need a negative 5 for the second component of the input vector. And once we have that in place, we can basically now determine what x has to be so that 3x plus y will equal 8. So you can write this off to the side and figure this out. 3x plus y has to be equal to 8, and we're saying y has to be negative 5. So x is going to have to be 13/3. Now we could repeat this process for any output vector that's in the xy plane. That's an important realization, because it's going to show that the range of this transformation is the entire xy plane. Okay, let's back up and talk about the domain. The domain is a set of all possible input vectors, and so we're allowing x and y, unless there are specified restrictions, we are allowing x and y to be any R2 vector. So the domain will be all of R2. The codomain is simply the parent space of the output vectors. And since the output vectors are 3-dimensional, we'll say the codomain is all of R3. But it's not necessarily the same thing as the range. The range are just those vectors in R3 that are possible output vectors, as the input vectors vary across all possible input vectors. And as we determined above, that the range of this transformation will only produce the entire xy plane in R3. Okay, let's look at the second transformation. This one inputs a 3-dimensional vector and outputs a 2-dimensional vector. So let's input the vector 1, 2, 3. So x is 1, y is 2, z is 3. Plugging that into our equations here for the output vector, we get x minus y, that'll be 1 minus 2, or negative 1. And 2z plus 1 will be double the z coordinate, so 6 plus 1 gives us 7. Now I'm curious if it's possible to get any possible 2-dimensional output vector. So let's just make one up, say 5, 6. Is it possible to get this output? What would the pre-image of this vector be, or what would the input vector need to be? Well, in order to get the 6, we would need 2z plus 1 to be 6. So that would tell us that 2z has to be 5. Z therefore has to be 5 halves. So we need this third component to be 5 halves. Now for the x and y components of our input vector, we just need to pick any two such that x minus y will produce that 5. So for example, I can pick 7 and 2 as the x and y components. So every single possible vector you could write right here does have a pre-image, meaning there is a 3-dimensional input vector I can find that will lead or map to that image, will map to that 2-dimensional vector 5, 6. All right, so the domain of this one is the set of all possible input vectors, so we're allowing that to be all of R3. The codomain is simply the parent space of the output vectors, and the output vectors are 2-dimensional, so we'll just say it's R2 is the codomain. But we've also just established that the range is also all of R2, because every single R2 vector possible, you put any vector right here, and you will be able to find a pre-image for it. You will be able to find a 3-dimensional vector in the domain that maps to that 2-dimensional vector in the range. So here's a case where the codomain and the range are the same. That's not always the case. We saw over here that the codomain and range were not the same. Okay, let's go to the next page. A transformation T from Rn to Rm is a linear transformation if the following holds true. So the transformation must have a linear property of that the same linear combination of input vectors will produce the same linear combination of output vectors for any input vectors u and v and for any scalars a and b. Then what we have is a linear transformation. Notice a special case of this. If I were to choose to let a and b, both scalars, be 0, then the input vector would also just be a 0 vector. So this would suggest that if you input the 0 vector into a linear transformation, the output vector should be, change both of these coordinates here to 0, and it doesn't matter what the images of u and v are. When you scale them by those zeros, you're going to get a 0 vector output. Now these two 0 vectors are not necessarily the same dimension. This first 0 vector is in Rn, and this output vector is in Rm. But what matters is that if you input the 0 vector into a linear transformation, you are guaranteed to get a 0 vector out as the output. That's not true for every transformation, but it must be true if your transformation is linear. Now let's determine whether the two transformations below are linear or not, and these are the same transformations from the previous page. To prove that a transformation is linear can be a little more tedious than to prove it's not linear. I will tell you now that transformation 1 will be a linear transformation, but transformation 2 will not be, and we'll establish our reasons for saying that. To prove that this transformation is linear, we basically have to establish this statement right here is true for all scalars a, b, and for any input vectors u and v. So we'll do that now by beginning with finding what this left side of our equation will be, and then we'll calculate the right side of the equation, and then we'll see that they're the same in the case of T1. So looking at T1 of AU plus BV, I'm going to replace U with U1, U2 as its components, and V with V1 and V2 as its components. And then I'm going to combine these vectors into a single vector before I plug it into the transformation. So we really have, the first component will be AU1 plus BV1, and the second component will be AU2 plus BV2. Now I have an input vector I can plug into the transformation. This transformation will produce a 3-dimensional vector where I triple the x-coordinate of the input vector. So we're going to triple this AU1 plus BV1, and then add to that the y-coordinate of the input vector, which is AU2 plus BV2. The middle component will be the opposite of the y-coordinate of the input vectors. So the opposite of AU2 plus BV2. And then the third component will be 0. Here's my 3-component output vector. I'm not going to go much further with this. Let's now compare this result, though, to what happens if I do A times the output vector when U is the input vector, plus B times, and then we'll do the image of vector V. So this will give us A times, and then we need a 3-dimensional vector when I input U. U is the vector U1, U2. Input that into this transformation right here. So we triple the first coordinate, so we'll have triple U1, and then add the second coordinate, so plus U2. The middle coordinate will be the opposite of U2, and then the third coordinate will be 0. So this is the image of U, plus B times, now the image of V will be the same thing, but with V's. So 3V1 plus V2, negative V2, and 0. Now if I distribute the scalars across these and combine these into a single vector, we'll get the following. We get 3AU1 plus AU2 plus 3BV1 plus BV2 as the first component. The middle component will be negative AU2 and then minus BV2. And then the third component will just be 0. At this point right here, we can see that these two outputs are the same. This would be easy to notice if you distributed this 3, distributed this negative, maybe reordered some of the terms, and then you can see that we have the same result. So because of this, we know that T1 is a linear transformation. Notice also that if I had plugged in the 0 vector into T1, that we would get the 3-dimensional 0 vector back. So this does satisfy that the image of the 0 vector is also a 0 vector, or the pre-image of a 0 vector is a 0 vector. Basically, if you input the 0 vector into this transformation, you get the 0 vector back. This must be true for all linear transformations, although this isn't a sufficient condition, but it is a necessary condition. There are transformations that are not linear, where if you input the 0 vector, you get the 0 vector back. Look at T2. T2, what happens if I input the 0 vector? So T2, let's input 0, 0, 0. The 3-dimensional 0 vector gets inputted, and let's calculate the 2-dimensional vector we get back. If all the components of the input vector are 0, then the first component of the output vector will be 0, because we have 0 minus 0. But the second component of the output vector will be 2 times 0 plus 1, which is 1. This is not the 0 vector. So right away, we can disqualify the second transformation as a linear transformation. Let's also disqualify it by giving a counterexample. Basically, you can let U and V be any two vectors you want. Let's let U be the vector 1, 2, 3, and V be the vector 1, 0, 0. So the I vector, standard basis vector. And let's let A and B both just be scalars 1 for simplicity's sake. So if I take T2 and I plug in my scalar A times vector U plus scalar B times vector V, let's simplify the input vector first, and then we'll plug it into the transformation. So this will be the transformation of, in our input vector. Since A and B are both 1, we're just adding U and V together. So if I add the two vectors U and V together, we get the vector 2, 2, 3. And when I plug this into my linear transformation rule, the first component of the output vector will be 2 minus 2, which is 0. And the second component will be 2z plus 1, which winds up being 7. But now let's compare this to what happens if I do A times the transformation of just vector U, so the image of vector U, plus B times the image of vector V, given this transformation. A and B are both 1 in this case, so I'll just erase them. Plug U into the transformation. So we subtract the two first coordinates. We do 1 minus 2, and we get negative 1 as the first component. And we double the third component, add 1. That gives me a 7. Now let's add to that. Let's add the image of V. So plug V into this transformation. The x-coordinate of vector V is 1, and the y-coordinate of vector V is 0. Plug them into the rule for the transformation. We get 1 minus 0, which is 1. And then plug in 0 for Z into the second component formula, and we get 1. So the image of V is the vector 1, 1. But when you add these two together, we now get the vector 0, 8. And because we did not get the same vector, this is a good counterexample, suggesting that this transformation is a nonlinear transformation. Okay, let's go to the next page. Consider a linear transformation T that maps R3 to R4. So the input vectors here are in R3. So let's let U be an input vector. To be an input vector, it has to have three components. So U1, U2, U3. And I'm going to decompose this into scalars times the basis vector, standard basis vectors. So this is the same thing as just doing U1 times the I vector plus U2 times the J vector plus U3 times the K vector. Now we're assuming that this transformation is linear, which means if I take the transformation and I plug the vector U into it, and then I rewrite U in this way of U1 I vector plus U2 J vector plus U3 K vector, that because this transformation is linear, I can basically distribute the transformation T symbol to all the interior vectors and factor the scalars to the front. So I can write this as U1 times the transformation of just the I vector plus U2 times the image of the J vector, which is T of J, plus U3 times the image of the K vector. Now keep in mind that these images here, these are vectors in 4 space. These are all 4-dimensional vectors because they're the images of 3-dimensional vectors. And in this case, our transformation T we assumed was mapping to R4. So this is really just a matrix vector multiplication where the orange vectors I have highlighted are the columns of a matrix. And then we multiply this by the scalars, which is just the vector U again. So this is a matrix here, and it is dimensions. Each of the images, each of the columns is a 4-dimensional vector. So we have 4 rows, basically, and then we have 3 columns. So it's a 4 by 3. Of course, this vector here is a 3 by 1. And then looking backwards, this image of the vector U should be a 4 by 1. And so the matrix vector arithmetic, keeping track of the dimensions, works out. All right, the consequence of this analysis in this specific case is really that every linear transformation from Rn to Rm has a unique matrix A that is an M by N matrix, such that doing T of U effectively amounts to doing that matrix times U. So all linear transformations can be thought of as matrix vector multiplication. Now this matrix is called the standard matrix of the linear transformation, and it is denoted, you put the transformation symbol T in square brackets. Furthermore, the columns of the standard matrix are the images of the standard basis vectors. This sentence is very important and very helpful, which we're going to use this idea multiple times. And looking at our work above, you can see that the first column right here is the image of the first standard basis vector. The second column is the image of the second standard basis vector. And then the third column is the image of the third standard basis vector. This pattern will hold for all linear transformations. Find the matrix T in brackets for the linear transformation below. So in other words, find the standard matrix of this linear transformation. Well, all we have to do is figure out the images of the standard basis vectors, and those will form the columns of the standard matrix. So for example, let's take this transformation and plug in the I vector. In other words, we're doing the transformation of the vector 1, 0. X is 1, y is 0, and the output vector will be x is 1, y is 0, so we get 3. X is 1, y is 0, so we get 0, and then the bottom one is always 0. So here's the image of vector I. Now let's look at the image of vector j. So we're going to map the vector 0, 1 to a new vector, and that vector is, plug in 0 for x and 1 for y, and we get 1, negative 1, 0. These two images become the columns of the standard matrix for this transformation. So we put capital T in these brackets to stand for its matrix, and its matrix is constructed by putting the image of I as the first column, so 3, 0, 0, and then the image of j is the second column, 1, negative 1, 0. What this means is that when you input any vector into this transformation, you can get the output vector by multiplying that input vector by this matrix and putting that input vector on the right side. Now in this case, there was arguably an easier way to do this. You could decompose the general image of any input vector. And decompose this, if I insist that each component of the image involve both x and y, then I could rewrite this output vector as 3x plus y, 0x minus y, and 0x plus 0y. And then I just decompose this according to whether it's a coefficient of x or y, factor out the variables. So we basically have x times the vector 3, 0, 0, plus y times the vector 1, negative 1, 0, which can be thought of instead as matrix vector multiplication, where these vectors become the columns of a matrix, and then the x and y become their own vector off to the side. Both methods work really well in this case for determining what that standard matrix is. All right, let's go to the next page. Now we're going to explore several linear transformations from R2 to R2. We're going to identify what the standard matrix is for each transformation, and then we're going to give the image of the given vector. Okay, so let's suppose a linear transformation wants to reflect a vector across the x-axis. All we have to do is track what will happen to the standard basis vectors to construct the standard matrix for this. So the two vectors displayed here are vectors I and j. These are our two standard basis vectors for R2. And we are going to perform the action described here to each of these vectors and see what the result would be. So let's begin with a vector I. Take this vector and reflect it about the x-axis. Well, this vector is already on the x-axis, so there would be no reflection involved. And so in this particular case, this vector would map nowhere. So the green vector I'm going to write here, this is the image, meaning the result of performing the action on the I vector. However, the j vector ends at the point 0, 1, and we're going to reflect that point to the other side of the x-axis. So the image of the j vector would be this red vector. All you have to do is determine what these two standard basis vectors will map to, and that's how you can construct the standard matrix for this transformation. So the first column will be the components of the green vector, which is the image of I, which happens to just be I in this case, because that vector was unaffected by this transformation. So its components are 1, 0. But the red vector has components 0, negative 1. These together form our standard matrix for this transformation. Specifically, if I begin with an input vector that's 2, 1, and I say do this transformation, visually, if you take the vector 2, 1 and reflect it to the other side of the x-axis, it should just become 2, negative 1. This is what we anticipate. So here I am getting my answer by just understanding what the action is, reflecting the point to the other side of the x-axis. But we can also arrive at this answer by doing this product of the standard matrix times the input vector. So basically, I would put the input vector here, 2, 1, and then I would just do matrix vector multiplication. And when you do this, you do get the result 2, negative 1. So if ever you want to perform a transformation that reflects a two-dimensional point to the other side of the x-axis, you just have to multiply that vector by the standard matrix of the transformation. Or let's say you want to reflect a vector across the y-axis. Well, in this case, the image of the vector I, which points to the right, if you reflect that to the other side of the y-axis, the image of I will be this vector here. But the image of the j vector will not change because it's already on the y-axis. So making a matrix out of these images, I was reflected and became negative 1, 0, and the vector j was not moved by the transformation, so it stays at 0, 1. So if you take this vector 2, 1, and you multiply it to this matrix, you will get the result, negative 2, 1, which has the effect of taking the vector 2, 1 and reflecting it across the y-axis. If you want to do a transformation that scales a vector by k, very simply you can just multiply the vector by the scalar k, but we can also represent this as a linear transformation where we multiply by an appropriate matrix. We'll just track what happens to the I and j vectors when you scale by k. So if you scale the I vector, it'll become k times the I vector. And if you scale the j vector by the same amount, it'll become k times the j vector. So the images, I becomes k0, and the image of 0, 1 will become 0k. So if you take this matrix and you multiply it by any vector, including the vector 2, 1, it will yield the vector 2k, comma k, which is the same thing you would get if you simply just did k times the vector. So we're seeing scaling by k can be done by multiplying by a scalar k or by multiplying by an appropriate transformation matrix, which is basically k times the identity, as k is on the main diagonal, zeros everywhere else. Okay, project to the x-axis. To project to the x-axis, let's just look at the point 2, 1. means really just remove the y-coordinate. So we want a transformation that'll turn 2, 1 into 2, 0, which puts that vector projects it down to the x-axis. Well, let's track what happens to the basis vectors. Well, I is already on the x-axis, so it'll project nowhere. So the first component will be 1, 0. But the j vector is 0, 1, and you project that to the x-axis. Just move the point vertically down till it's on the x-axis. And the projection of the j vector is just going to be the origin. So the 0 vector is the image of the j vector. So the 0 vector is where the j vector gets mapped to, so that becomes the second column of our transformation matrix. And we have this simple matrix here. If you multiply this matrix by any vector, such as 2, 1, you will see that this will have the effect of basically zeroing out the y-coordinate but keeping the x-coordinate. And it's called a projection of the vector to the x-axis. If you want to project a vector to the y-axis, then the point 2, 1 should project to the left of the point and become the point 0, 1. Basically, you just want to zero out the first coordinate, but keep the second coordinate. We'll track what happens to the basis vectors. The I vector, which is not on the y-axis, it ends right here, will be projected to the y-axis, so it'll shrink to the 0 vector. This is the image of I. It's the 0 vector. But the image of the j vector will go nowhere because it's already on the y-axis, so projecting it to the y-axis changes it not. And so we put the first column with the image of the I vector, which is the 0 vector, and then the second column is the image of the j vector, which is still the j vector, so still 0, 1. And this becomes our standard matrix for this transformation. And if you multiply any vector times it, so multiply it by 2, 2, 1, you'll see this will have the effect of zeroing out the x-coordinate but keeping the y-coordinate. So it also yields this result. And now we're going to explore a little bit the trickiest of our two-dimensional transformations in this lecture, which is a rotation counterclockwise by theta. So this would be a case where you have some sort of a vector, but then you want to rotate it to a new position. Rotate it by an amount theta, and we're going to go counterclockwise. Well, we have to track what happens to the I and j vectors when I rotate them by an angle of theta. I'm going to draw a unit circle on here. If we rotate the I vector by an angle of theta, it'll be, I will just draw it here in the first quadrant, but here's will be the image of it. And this would correspond to a rotation by theta. Now we're on the unit circle here, so it means that the coordinates of this vector would just be the cosine of that angle and then the sine of that angle. So the I vector would rotate and would now be at location cosine theta, sine theta. If you take the j vector and rotate it by the same amount, theta, counterclockwise, then its image will be this vector. There are many ways to determine what the components of this new red vector will be. We know that the red and the green have to be perpendicular, so whatever the coordinates are, if I find their dot product, I should get 0. You might also remember that the slopes of perpendicular lines are negative reciprocals of each other, and you can find the slope of either of these lines by doing the y-coordinate divided by the x-coordinate, or you can look at some similar triangles here because we will make some similar triangles. Its components are going to be negative sine theta, cosine theta. I will point out that if you take this vector and you dot product with this vector, you will get 0. Furthermore, the slopes are negative reciprocals of each other, and based off similar triangles, if this is cosine of theta, I'll just say c theta, and this is sine theta, I'll just say s theta, then by similar triangles, we know that this had to be negative sine theta and this had to be cosine theta. So there's a variety of ways in which we might confirm that this is in fact the correct coordinates of the image of the j vector. This allows us to construct a standard matrix that's going to look a little bit clunky, but the first column will be the components of the image of the I vector, so there will be the cosine theta and sine theta, and then the second column will be negative sine theta and cosine theta. So you would first choose theta, and then you would plug theta into these expressions, and that would give you the standard matrix of the transformation needed. So if you take this matrix and you multiply it by the vector 2, 1, for example, this will yield the result of doing this transformation, which is equal to, do matrix vector multiplication, so the 2, 1 would go here, and then you would drop the 2, 1 onto these rows, multiply, and then add corresponding results. So that would give us the result 2 cosine theta minus sine theta is the first component, and the second component would be 2 sine theta plus cosine theta. I do want to explore this one with technology, so let's go over to, I'm going to use GeoGebra, but GeoGebra 2D for this. And I have typed in the vector u, 2, 1. I've created a slider t, and I changed its limit so it ranges from 0 to 2 pi. Then I typed in a matrix, I'm calling it matrix A, and it's cosine, t stands for theta basically, so we have cosine theta, sine theta, and negative sine theta, cosine theta, and then it plugs in this value t and calculates it, so you can see we have a rather unpleasant looking 2 by 2 matrix. But then I take that matrix A and I multiply it by the input vector u. And now let's reveal this. And I'm going to drag the slider to various amounts. So if t is 0, it means we don't do any, we rotate by 0 degrees. All these t's to zeros and calculate these trig functions, you will get the identity matrix. And multiplying u by the identity matrix doesn't change it, so we still get this same result. But as soon as I change t, the angle, to other amounts, you'll see us getting different results. And as t continues to move, I'll just hit play, you'll see our rotation happening until we rotate all the way around. We get to t equals 2 pi, and then it starts over. Now we have the tools. If you want to rotate a different vector, let's say we start with the vector 2, negative 3. So this is our beginning vector, and now I will rotate that vector instead by an angle of theta. Okay, let's go to the next page. The next page is a summary of some standard transformations from R3 to R3. Looking at the first column, if you want to reflect a three-dimensional point around the xy plane, that means you basically just want to change the sign of the z coordinate. So we know that this vector should become the vector 1, 2, negative 3, and this would produce a vector that have been reflected about the xy plane, reflected across the xy plane. Change the sign of the z coordinate. Well, to find the matrix for this transformation, you simply have to imagine what will happen to the I, j, k vectors when you do this same transformation. So the I vector is already on the xy plane, so it won't go anywhere. So the I vector will map to itself. Its image is itself. The j vector is also on the xy plane, so it also will map to itself. But the k vector, which is 0, 0, 1, that's 1 unit above the xy plane, will reflect to 0, 0, negative 1. So that reflection, or that image, is the third column of our transformation matrix. And sure enough, you can verify if you multiply the vector 1, 2, 3 times this matrix, you will effectively just change the sign of the z coordinate. Right, to reflect about the xz plane, you change the sign of the y coordinate. So this will produce the vector 1, negative 2, 3. Standard matrix for this transformation. Let's begin by thinking about the I vector that's already on the xz plane, so it's not going to map anywhere. The j vector, though, is 1 unit to the right, points 1 unit to the right of the xz plane, so the j vector will map to 0, negative 1, 0, instead of being 0, 1, 0. And the k vector is already on the xz plane, so it's not going to map anywhere. It stays the k vector. And sure enough, if you take this matrix and multiply it by the vector 1, 2, 3, it will have the effect of simply changing the sign of the middle coordinate. You're starting to pick up on a pattern here, and the reflection about the yz plane will have the effect of changing the sign of the x coordinate, so its standard matrix will be as shown here. You multiply any vector to this matrix, and it will have the effect of changing the sign of the x coordinate, which visually is a reflection about the yz plane. All right, let's do projections. If you take a vector and you project it to the xy plane, that basically just means zero out the z component. So this vector 1, 2, 3 should become the vector 1, 2, 0. The matrix for this transformation, well, the I vector is already on the xy plane, so it's not going anywhere. The j vector is already on the xy plane, so it's not going anywhere. And then the k vector, though, is 0, 0, 1. It needs to project down to 0, 0, 0. And sure enough, take this matrix and multiply it by any vector, such as 1, 2, 3, and it will have the effect of zeroing out the z component, but leaving the x and y components untouched. The other projections are similar. If you want to project to the xz plane, you zero out the y coordinate, and if you want to project to the yz plane, you zero out the x coordinate. And we have the standard matrices as shown below. Now let's explore the rotations, a little bit more complicated. If you want to rotate about the x-axis by theta, let's first show with technology what that means. Okay, so I've plotted the vector 1, 2, 3. It's 1 in the x direction, 2 in the y direction, and then up 3 units. Now I'm going to rotate this around the x-axis. The x-axis is the red axis. So imagine the plane x equals 1, and you can see the vector hits that plane. We're going to rotate around the x-axis, meaning that I'm going to want to take this vector and rotate it, but keeping it in the plane. So I don't want to change the x-coordinate. I just want to rotate in such a way that it's the y and z coordinates that are changing. So you'll notice I'm creating these red vectors that you're seeing here. They're rotating around the plane. And if you look at this straight down the x-axis, so that you see the y and z axes, y-axis to the right, z-axis up, it looks like just a regular rotation in two dimensions, rotating counterclockwise. All right, back to our notes. To accomplish this, we're just going to reveal the standard matrix for this transformation. If you want to leave the x-coordinate the same, then put a 1 in the top left position. And if you want to rotate around the x-axis, so this will have the effect of rotating the y and z coordinates basically, then you put the same transformation matrix we had up here for 2 dimensions, but you put that down in the lower right corner. So we're going to put cosine of theta, sine theta, negative sine theta, and cosine theta. And the other entries are going to be all zeros. Multiplying a vector by this matrix will have the effect of doing a rotation about the x-axis. Now let's say you want to rotate about the y-axis. Let's go back to technology. All right, so we have our point 1, 2, 3, and on the y-axis is the green axis. So I want to rotate this point around the y-axis. The vectors, as it rotates, we want to keep the y-coordinate the same. Let me go ahead and reveal that plane. That's the plane y equals 2. So we're going to rotate this now around the y-axis while keeping the vector on that plane. All right, let's look straight down the y-axis, but in such a way that the x and z axes are oriented normally. So we have the x-axis pointing off to the right, the z-axis pointing up, and effectively this looks like, therefore, we're just doing a basic 2-dimensional rotation of the vector counterclockwise. But in a 3D context, we're just rotating the vectors so that they stay in the plane as we rotate around the y-axis. Okay, now the matrix for this one is going to be similar to this matrix. This transformation matrix now is just going to be relocated in our 3-dimensional grid here. It'll be spread out so that the 4 trig functions are in the corners. We'll have a 1 in the middle and then zeros everywhere else. This matrix will have the effect of keeping the y-coordinate the same, but rotating the x and z coordinates. And now let's look about what it means to rotate about the z-axis by an angle theta. So again, we have our vector 1, 2, 3, and we're going to rotate around the z-axis. So this point is going to rotate around the z-axis, maintaining always the same z-coordinate though, and that z-coordinate is 3. So let me reveal that plane, z equals 3, and we'll look at it from below. So as this vector rotates, it'll stay in the plane and it'll just rotate around the z-axis. So let's look straight down the z-axis in such a way that we can orient it so the x and y axes are in their normal orientation. So the x-axis pointing to the right, the y-axis pointing up, and looking straight down this, it looks like a 2-dimensional rotation. To construct this matrix, I want to keep the z-coordinate the same and want to do the rotation on the x and y. So this rotation matrix gets put in the upper left corner instead. We put a 1 in the 3, 3 position and then zeros everywhere else. And multiplying a vector to this matrix will have that effect. It will keep the z-coordinate the same, but we'll rotate the x and y coordinates about the z-axis. The programming I used to animate the rotations in 3D are linked to the home page in Canvas for your exploration. Let's go to the next page. Now, like any functions, linear transformations can be composed, meaning you can do one after the next. Consider the linear transformation, T, maps R2 to R2, which does the following sequence of actions. So we'll break this down into 3 different transformations one at a time. So T1 is the action of scaling by a scale factor of 2. T2 will then rotate 30 degrees counterclockwise, and then T3 will project to the x-axis. So let's get a sense for what's going on visually, and then we'll talk about all the matrices that are required to accomplish this. So down here, we have the vector 2, 1 in our image down here. We're going to scale this by a factor of 2 to begin. So we're going to double its length. It should now end at the vector 4, 2. Then we're going to rotate this vector 30 degrees counterclockwise. So I'm just going to draw a rough image of what this might look like. So the length of the vector won't change, but we'll go 30 degrees in the counterclockwise direction, and then we'll have a new vector like this. And then finally, the third transformation was a projection of this vector to the x-axis. So wherever the tip of this is, we're just going to go straight down to the x-axis, and this vector here should be our final result of the sequence of transformations. Let's see if we can determine what exactly are the components of this orange and final vector. Let's begin by first determining the correct standard matrix for T2, the rotation. So the standard matrix for T2, to rotate 30 degrees counterclockwise, we do cosine of that angle. So we'll have cosine of 30 degrees, and then sine of that angle will be the first column of this matrix, and then negative sine of this angle, and then cosine of this angle. And this is a 2 by 2 matrix. Let's go ahead and simplify these results. We can refer to the unit circle to get what these values are. The cosine of 30 degrees is rad 3 over 2, and the sine of 30 degrees is 1/2, giving us this 2 by 2 matrix here. This is the transformation matrix we are going to use to accomplish the 30-degree rotation in the counterclockwise direction. So beginning with the vector u, we'll do the first transformation we'll say is the red transformation. It made this red vector down here. Well, this is transformation T1. And to scale a vector, the matrix that we would use would be the identity matrix, but with the scale factor on the main diagonal instead. And if this is vector u, and I multiply that vector right here, 2, 1, and do this matrix vector multiplication, I do get a new vector, and that vector will be 4, 2, which is our red vector in our image. Next, we're going to do the rotation. So this will be transformation 2. To accomplish the rotation, we're going to multiply this red vector by this matrix right here. I'll just copy it and multiply this by 4, 2. This will produce the vector that is green in our image. So the 4, 2 go here and here, and we do matrix vector multiplication, and we drop them down. So we have 4 times rad 3 over 2. That's going to give me a 2 rad 3, and then minus 2 times 1/2, so minus 1. Now take the 4, 2 and drop it down onto the second row and multiply. 4 times 1/2 is 2, and 2 times rad 3 over 2 is just rad 3, so plus rad 3. This is the 2 by 1 vector that you see depicted in our image below, the green vector. Now finally, we want to do the third transformation, transformation T3. Well, to project a vector to the x-axis, we want to zero out the y-coordinate. So the standard matrix for this was the matrix 1, 0, 0, 0. And we're going to multiply this matrix by this green vector here, and this will produce first coordinate only and zeroes out the y-coordinate. And these are the components of the orange vector in our image below. So taking a step back and looking at this process, to do the ultimate transformation from start to finish, we'll call that just T without a subscript, and if we input the vector u, then we had to do the following sequence of multiplications by matrices. We first multiplied vector u by the standard matrix corresponding to transformation T1. We did this first. That gave us the red vector. And then we multiplied that by the standard matrix for the second transformation. This ultimately produced the green. And then we finished by multiplying all of this by the standard matrix for the third transformation. So this was the sequence of matrix multiplications we did, and notice how we have them written. The one closest to u is what we do first, and then we work from right to left. So it's the standard matrix for T1, and then the standard matrix for T2, and then the standard matrix for T3, working that way. But matrix multiplication is associative, so I can reorder this, and instead I can do the following product. I can multiply the 3 standard transformation matrices together first, and then multiply all that by vector u. Let's go ahead and multiply the orange and the green standard matrices together first. So the first column we get rad 3 over 2 plus 0, so just rad 3 over 2, and then we get the 0 vector. And then for the second column, we're going to get negative 1/2 plus 0, and then the final entry just zeros. And now let's multiply these final 2 matrices. We're going to get rad 3 plus 0, so just rad 3, and then 0. And then for the second entry, we'll get negative 1, and then 0. And then times our vector u. Now u was the vector 2, 1. This is the vector that we wanted to transform ultimately. And when I do this final multiplication, I do get as my first component 2 rad 3 minus 1, and the second component will be 0. Where this was the same result we got up above. So it's the product of these 3 standard matrices that yields the standard matrix for the entire transformation. Standard matrix of the transformation T is this 2 by 2 right here, which was the product of the 3 standard matrices for the 3 separate steps. All right, this concludes our discussion on linear transformations.